going to teach conductor rules. Conductor rules. Okay. Before we start getting into Gauss's law and further with this AP Physics C E&M content, let's talk about some special conductor rules that we're going to need to know moving forward. Okay, and there's 4 rules here. You should write these down. You should burn them into your memory. They're very important for us. First is that any excess charges are always located on the surface of a conductor. So if I have a conducting sphere here, all of the excess charges that make up, it's got a charge of positive Q, they're all on the surface. Okay? Even if this is like a solid ball, like if this is a solid copper ball, all of the charges are on the surface. All the excess charges are on the surface. So whatever is giving it this positive Q, those charges are on the surface only. Okay? And the reason why this is due to the second part here. Given a conductor in electrostatic equilibrium, like this ball with some charge Q on it, it only makes sense that there's no electric field within the conductor itself. And the reason why this is the case is that if there was an electric field in here, as given by the great Novak from 2017, one of my students, if there was an electric field in here and I had a charge on the inside then the charge would get pushed to the outside. Or that you'd have to have multiple charges in here to push each other, and the charges would fly away. So you can't have that. The electric field on the inside is going to be 0. Even if this is a solid sphere. Why was that so hard? Even if it's a solid sphere, all of the charges are on the outside, so the E field on the inside is 0. Another way we can see this is given a number of methods, either solid angles, Gauss's law, the shell theorem. The net force in E field inside a hollow conductor is 0. So if you have a hollow conductor here, all of the charges are on the outside. And we'll see this when we talk about Gauss's law next, and this will make a ton of sense. But if you make a Gaussian surface on the inside here, you haven't encapsulated any charges, so the E field is 0. And this is also why if we go up here, this E field also has to be 0 because there's no charges on the inside. Okay? You would have to have some other non-conducting object like an insulator to do that. But we are talking about conductors. And there's no E field on these conductors because the charges lie on the outside. Okay? Because of this, all points within the material of a conductor are at an equipotential. The voltage inside a conductor is the same everywhere. And one reason you know that is because an electric field is equal to the negative derivative of the voltage or of the electric potential as a function of radial position. If your electric field is 0, then your derivative will be 0, which means that all of these voltages are at some value. Or rather, and I stand corrected by this, your voltage here, the derivative of the voltage has to be a 0, which means you're taking the derivative of a constant with respect to position. Okay, so when you take the derivative of a constant, you get 0. So since the E field is 0 on the inside, the voltage can be a number. Okay, it can be a number, within this conductor, but it is that number everywhere within the conductor. And that's because when you take the derivative of that constant, it has to be equal 0 based off of this equation. Okay, so that's what's going on there. One last thing, and it's kind of a side note. If you sum the voltages through a closed loop, the sum of the voltages through a closed loop is going to equal 0. And we've actually talked about this in a more like circuit sense, because when you do a Kirchhoff loop, you sum all of your components and set them equal to 0 at the end. This is because we're running through a closed loop of conservative forces and fields, which cause this to be true. Okay, so this is just something to mathematically that matters. We're not really concerned ourselves much with it, but it does pop up for the Kirchhoff loop, which is a nice helpful thing for us. Okay. So these are the 4 things in the side note that are very important. Remember, those charges are always on the surface of the conductor. There's no E field within the conductor, even if it's solid. If it's hollow, it's still 0. The E field is still 0 inside a hollow cylinder, and that means that for all intents and purposes, and for all purposes, the points inside the material of a conductor are at an equipotential. Even if it's solid, even if it's hollow, the voltage will be a constant value there, and that will be it. Okay, it could be 0, could be positive, could be negative, whatever it is, it's just a value. Okay, so these are some things to keep in mind as we're going forward. These rules will begin to make a little bit more sense when we start talking about Gauss's law, which we'll do in the next video. We'll talk about flux and intros to that. But for right now, know these. But this is finished. Adios, and everybody, take it easy.